In this video we will be talking about the meter, which is the SI unit for length. So in the ancient times, two well-known units were known for measuring length, and that was the cubit and the foot. Was the cubit and we have foot. So the cubit was the length from your middle finger's tip to the elbow below, to the bottom of your elbow, the length, and it was used by ancient Egyptians and was used also by ancient Indians. It was the length from the tip of your middle finger to your elbow bottom, to the bottom of your elbow. And then foot, we have foot, and foot was used in ancient Greece. It was used in ancient Greece, and also it was also used in Rome. But as we know that these are based on human lengths, so it varied from person to person, and it was not selected as a universal unit for measuring length. So in 1671, Jean Piccard. So in 1671, Jean Piccard measured the length of a seconds pendulum at the Paris Observatory. He measured the length of seconds pendulum. So he measured the length of a seconds pendulum. So what is seconds pendulum? So seconds pendulum is the pendulum that has time period of 2 seconds. It has time period of 2 seconds. So Jean Piccard measured the length of a seconds pendulum, and he proposed that this should become the unit for measuring length. But soon the French astronomer Jean Richer measured the length of seconds pendulum and found a 0.3% difference. Difference in length between Cyan and Paris. Between Cyan, which is in French Guyana, and Paris. So Jean Richer found out that there is 0.3% difference in length between from Cyan, which is in French Guyana, and Paris. So 0.3% difference looks like a very small difference, right? But when you are actually measuring bigger and bigger quantity, bigger and bigger lengths, it becomes very noticeable. So it was just a no-go for them. And also also in high school you have studied the time period of a pendulum, which is T equal to 2 pi square root of L by G. So G differed from places to places, not in a greater manner, but in a small manner. So this was also second pendulum idea was also thrown off due to 0.3% difference. So as a result of the French Revolution, so at the time of French Revolution, at the time of French Revolution, the French Academy of National Sciences, um, the French Academy of National Sciences charged a commission to create a single unit, a single scale for measuring the length. So um, just let me write it down first. The French Academy of Sciences. The French Academy of Sciences charged the commission to um, they charged a commission they charged a commission to to find a scale to measure the length. So in 1971, oh sorry about it, in 1791, in 1791 the French Academy of Sciences declared that um, a 1 meter will be one tenth 1/10 millionth of of the distance from North Pole, from the equator to the from the North Pole, and the line should be passing through Paris. So in 1991, here is the diagram. Here is the figure. So what was the meter? According to in 1791, according to the French Academy of Sciences, a meter should be 1/10 millionth, which is 1/10000000 of the distance between the equator and North Pole. Measured along meridian passing through Paris. So that was their definition for the meter. So the next step was to measure that distance. So there were two surveyors who actually calculated the distance, and these are the two surveys, and these are is Pierre McCain, and we have Jean Baptiste Delabre. The two surveyors, Pierre McCain and Jean Baptiste Delabre, they calculated the distance, and at the meantime, also not to mention that they took around 6 years, 6 years from 1792 to 1798. They took approximately 6 years in order to calculate the distance. And at the meantime, while knowing the approximate result, the Commission ordered several platinum bars of meter which had slightly different lengths, and when Jean Baptiste Delabre and Pierre McCain had the calculations, when their calculation was completed, the different meter, the platinum meter boards which had the approximate, which has the closest result to the calculations, was selected as a meter, and that became as meter des archives. So it was placed in, and that selected meter was placed in National Archives in 22 June 1799. And that meter bar came to known as meter. Let me write it down. Meter des archives. So, as the definition and a physical object now ready to measure the meter, a lot of countries also adopted the metric system and also adopted the meter also. But it soon came to realization that the meter des archives was not exactly the 1/10 millionth of the distance between the equator and the north pole, and also the fact that these two surveyors' calculation were wrong. So this also became a very big problem, as we also talked a few minutes ago, that the commission calculated some approximate results, and they created different platinum bars of meter of different lengths, and the calculation that was closest to the meter bar was selected as meter des archives. So the calculations were also wrong. Plus, it wasn't exactly it wasn't exactly 1/10 millionth of the distance. So that was also a problem. So it became a need to develop another meter bar. So in let me just okay, in 1889, the first general conference on weight and measures, the first I will just use the words, the first general conference on weights and measures, the International Bureau of Weights and Measures um, established an international prototype meter, developed another per meter that was known as International Prototype Meter, and and it was and and it was the distance between two lines on a standard bar of an alloy made of 90% platinum and 10% iridium, provided that it was at the temperature of melting point of ice. So at the in 1885, 1890, 80, in 1889, the first general conference weight and measures, the International Bureau Weight and Measures established that a meter should be, I think I should write it down, a meter should be the distance between the distance between two lines on a standard bar composed of alloy of 90%, let me just write it down, of composed of alloy of 90% platinum and and 10% iridium. At the melting point of ice. So this was the definition for the new meter and was known as the International Meter Prototype. And this is the International Prototype meter. This is the image. I'm gonna write it down. International Meter Prototype. So that solved the problem for the that was occurring in the first meter, that was meter desk archives, and International Meter Prototype solved that problem. But there was a problem also. The problem was that, of course, it was a solid piece, but it can decay over time. So the meter itself was changing. So they needed so the purpose of the meter was that it should never change. It should be the same at all times. So there was a need to have for a better for more accurate and more not changing meter. So at the era of interferometer, when interferometer was created, interferometer, we have another person here who is Mitchell A. Oh, who is Albert. Sorry about that. Albert A. Michelson. So here A stands for Abraham Albert Abraham Michelson. So he created the interferometer. So what is interferometer? The interferometer is an instrument that is used to calculate the wavelengths of radiation. So as we know, the meter was based on a physical object, and there was a need to have a better definition for it. So they wanted to shift from a physical object to a physical phenomena. So interferometer was used in determining the new definition of the meter. So Albert A. Michelson measured the International Meter Prototype with an accuracy of 0.1 micrometer. 0.1 micrometer from the red light of cadmium. So let me remove it and write it down in an organized manner. Albert A. Michelson measured the International Prototype meter with an accuracy of 0.1 micrometer, and using the red line of cadmium. Red line of cadmium. So as a result, in 1950s, in the 1950s, more experiments were done, because Albert A. Michelson, although he measured the International Meter Prototype with a great accuracy, but it was not accepted. It was not quickly accepted as the new definition for meter. So more experiments were conducted, and they found out that the orange line of krypton 86 was more stable than that it was more stable than red line of cadmium, the orange line of krypton 86. So as a result, in 1960s, in 1960s, at the 11th General Conference, I'm gonna keep it short, General Conference on Weights and Measurements. They defined the meter at in 1960 at 11th General Conference on Weights and Measurements, that a meter should be 1,650,763.73 wavelengths of orange line of krypton 86. So it was again changed to a new definition, but as compared to the older one was based on physical object. Now here it was based on physical phenomena. But also sorry about that, krypton 86 in a vacuum, to be more precise, in a vacuum. So in 1960 it was changed into a new but better definition, but still the people and scientists needed more accurate definition for a meter based on the natural constants, the constants of the universe. Like we have gravitational constant, we have Planck's constant. These are all universal constants, the natural constants. So they wanted a more accurate definition, more precise definition for the meter based on the natural constant, on universal constants. So as a result, at the so there were also progress made in lasers, in lasers. So when the era of lasers came, the scientists were calculating the speed of light very accurately, with great accuracy, using lasers when the era of lasers started. So and hence, as a result, with more accurate speed of light in 1975 at 15th General Conference on Weights and Measures, they they concluded to give the value of the speed of light as 299792458 meter per second. So in 1975, the General Conference on Weight and Measure decided to give the conventional value for the speed of light, and that was 299792458 meter per second. So with an accurate value for the speed of light, in 1983, oh boy, I cannot go down. Where's the scroll? So about it, I guess I have to write it down here. In 1983, the 17th General Conference on Weights and Measures. Let me just. Okay, you decided to show up now. Good. Okay. So in 1983, the 17th General Conference on Weight and Measures again updated the definition for meter, and that was the path of light traveled in a time interval of 1 by 299792458 seconds. So it is just basic math, I guess you can say. um, because in 15 general conference of weight and mayors, uh, they they gave the conventional value to the speed of light, and that is meter per second. This is the value of the speed of light, and that will be like, all right, in 1 second the speed of light is 299792458 meters, right? Now, to get the 1 meter, you just have to divide this value by 1, and this becomes 1 by 299792458 second, and the other side becomes 1 meter. So so now the current value, the best definition for meter is that the distance traveled by light in 1 by 299792458 seconds. So I hope you liked this video. I hope so, because it became too long, but I needed to to explain it in a little detail about how the meter came to be. So I hope you didn't find it too much boring. So in the next video we will be talking about second, because here we talked about the speed of light, and we also said in 1 second. So second is also a quantity, and second is also a unit for measuring time. So the speed of light couldn't be measured with the development for in the accuracy of second for measuring time. So how did we measure second, the SI unit for time, accurately? We will talk about in the next video. So once again, I hope you found this video informative and didn't got bored during my insane lecture, I guess. So please like this video and subscribe to my channel for more future videos. In the next video I will be talking about second, the SI unit for time. Thank you very much.